What if you could build and test a quantum computer right from your browser? The world of quantum computing promises to solve problems we once thought were impossible, but for most of us, it remains a complex, inaccessible black box. Today, we're changing that. Introducing QClassiQ. Learning quantum computing is hard. It requires deep knowledge of linear algebra, complex physics, and specialized programming languages like Qiskit. Aspiring developers and researchers spend countless hours writing boilerplate code just to set up a simple experiment, creating a massive barrier to entry. How can we expect to build a quantum future if only a select few can participate? QClassiQ is an intuitive, web-based platform that demystifies quantum computing. We've replaced complex code with an interactive, visual circuit builder. Our mission is to empower students, researchers, and developers to design, simulate, and understand quantum circuits without writing a single line of code. Let me show you how it works. Here is the main dashboard. In the middle, we have our controls. Let's start with a simple 2-qubit system. In our circuit builder, for the first layer, I'll apply a Hadamard gate to our first qubit, Q0. This puts the qubit into a superposition of 0 and 1. Next, in the second layer, I'll apply a CNOT gate, with Q0 as the control and Q1 as the target. This links the two qubits together. Instantly, our backend, powered by Flask and Qiskit, constructs the circuit, runs it on a high-performance quantum simulator, and sends the results back. Let's explore this quantum simulator. We'll start with a 2-qubit system and one layer of gates. For the first qubit, Q0, let's apply a Hadamard gate. For the second qubit, Q1, we'll select a CNOT gate. Okay, looking at the results, the circuit diagram has correctly ignored the CNOT, since that's a 2-qubit gate. It only shows the Hadamard gate on Q0. This should result in a 50-50 mix of the 2000 foot and 10 states. And for our next circuit, let's swap the Hadamard for a poly-X gate on the first qubit, leaving the CNOT on the second. Let's run the simulation. The circuit diagram now shows the X gate on Q0. And the result is a 100% probability for the 01 foot state. Here we're using a quantum circuit simulator, beginning with a 3-qubit, 2-layer configuration. And we see a new outcome. All 8 possible states now appear with a nearly equal probability. Let's make one final change to this circuit, switching a CNOT gate to a poly-X. The simulation result remains a uniform distribution across all 8 states. To finish, we'll increase the complexity to a 4-qubit system and design a new, more intricate circuit. This complex circuit results in an equally complex superposition, with various probabilities distributed across multiple quantum states. QClassiQ is more than just a simulator, it's a launchpad for the next wave of quantum innovation. For education, students can finally see how quantum mechanics works, turning abstract equations into interactive experiments. For research, scientists can rapidly prototype and test new quantum algorithms before committing to complex, code-based implementations. For everyone, we are lowering the barrier to entry, making quantum computing accessible to anyone with a curious mind and a web browser. The future will be built on the principles of quantum mechanics. With QClassiQ, we're ensuring that everyone has the tools to be a part of that future. We've built the bridge from classical intuition to quantum understanding. Thank you.